We'll use this DC power supply to supply current to our solenoid. The current comes out the red wire and goes into our slinky. That slinky is like a coil of wire, which is a solenoid. As it goes through the coil of wire, it creates a magnetic field. It comes out the other end and goes into an ammeter, so we can monitor the current. It goes from the ammeter to something called a rheostat, which is basically a variable resistor. You'll see why we need that later. All of these are in series, and the current goes back to our DC power supply. The current in the solenoid creates a magnetic field that runs along the axis of the solenoid. So you can see here, our magnetic field probe should be positioned right in the middle of the solenoid. I raised it up on a roll of tape so it sits right in the middle of the slinky. The way we'll carry out this experiment is by changing one variable at a time. Since the easiest one is probably current, we'll start with that one. I'll hook up the probes and count how many turns. I believe we have 20 here, and I'll measure the distance. So the number of turns and the distance between the connections stays the same. The only thing I'll change is current. The magnetic field sensor is set up to detect a magnetic field perpendicular to the probe or along the axis of the solenoid. To collect data for changing current, we'll set up the current, turn it on, and collect some data. Then I'll turn the current up and do it again. And I'll keep doing that until I have 5 or 6 data points. Next, we'll change the length. We'll keep the number of turns the same. We'll keep the current the same, but we can just move the two endpoints in and out to change the length. So this would be our short length. Put the probe in the center, take a data point with current flowing, measure the magnetic field. Then we stretch it out to a different length, measure it, set up the magnetic field sensor in the center of that solenoid, turn the current on, and take another reading. And we do that until we get 5 or 6 data points. Now we'll change the number of turns while keeping the length and the current constant. Let me show you why this is the trickiest change to make. I've just reduced the length of my wire by 5 turns. Wire has a little bit of resistance to it, especially the slinky. So I've reduced the resistance of my circuit and the current will run a little higher. I want to adjust that, but the controls on the DC power supply aren't that precise. That's why we have the rheostat in place. Every time I reduce the number of turns in my slinky, I can nudge the rheostat a little bit and increase the resistance until the current is the same as it was in the previous run. Of course, before I take any data, I have to fix the length. I told you I wasn't going to change the length. So every time I change the number of turns, I have to stretch that slinky to get the length to be the same as it was before. The company we purchase our equipment from for our labs is called Pasco. So our magnetic field sensor is made by them. And they have an interface box. The magnetic field sensor plugs into the interface box, and that converts the signal into something the computer understands as a magnetic field. We're going to use their software to help us look at the data and figure out what the field is due to the current in the coil. I'm going to select sensor data, and this is what the interface box looks like. I'll click on one of the interfaces. This is an analog input, A. I'll click on that one, and it brings up all the analog sensors that they sell. And I'll scroll down until I find the magnetic field sensor. So it knows the magnetic field sensor is plugged in to port A. I want to take a look at the settings here for that magnetic field sensor. It's set to a gain of 1x. That's good. That's what my sensor is set to. You can also get increased gain to look at smaller magnetic fields. Now I'll take a look at the data setup. I'll click here. There we go. Now I can take a look at the numerical format. The default is it only displays one significant figure. We don't want that, so I'm going to change the number of decimal places to 3. So it's displaying magnetic field strength in Tesla versus time. Now we're ready to record data. I try to follow the same procedure every time. That way you can look at the data and each data set looks familiar and you'll know what I did each time. I hit record. Then I reach over and about 3 seconds later I hit the tare button on the magnetic field probe. And then about 8 seconds I turn on the current and I wait about 4 to 6 seconds, turn it off, wait another 4 seconds or so, and hit stop. Now let's expand this. You can click on the scale and just stretch it, because our magnetic field is nowhere near this strong. We have to expand the scale to see what happened. So the reading started out at this negative number, and about 4 seconds I hit tare, and that zeroes the sensor, so it got it close to 0. And about 8 or 9 seconds I turned on the current, so now we're measuring the magnetic field due to the current in the wire. And then I turned off the current and we're measuring the magnetic field that's the background. I'll call it the background field, the magnetic field due to the Earth and other random fields that might be present on my table, near my table here. So we want to extract the data. We want to know how much magnetic field is due to the current in our coil. What I like to do is I'll come up here and click on this little crown thing. I think those are some data points that are highlighted. Not a crown, but you get the idea. And I select a couple of seconds before I turned on my magnetic field and a couple of seconds after I turned on my magnetic field. And I want to know what's the average. So I'll move this. That looks pretty good right there. I've got some points highlighted here in yellow and some points highlighted here in yellow. And I want to know what's the average. I'll click on this little sigma and it's telling me, it's displaying the average. So that's the average magnetic field with my current off. That's just the magnetic field that exists on my table here at this location in space with my current off. So I'll record that as the background magnetic field. Then I'll move this down. Do I need to expand that a little bit? That looks pretty good. And I'll take an average of the magnetic field with the current on, and I will subtract those to get the difference. You'll notice that one of them is positive and one of them is negative. That's just because of the direction of the current is creating a magnetic field that my magnetic field probe has defined as the negative direction. If I turned my current in the opposite direction, it would have been positive. So we'll subtract one from the other one, and that will be the magnetic field due to the current in the wire. In Excel, I'm going to make a table to record the data. So first, I'm going to change current. I've got a length in centimeters, number of turns, and current in amps. I'm just going to do a quick example here. My length is 40. I'll do 3 data runs. The number of turns is 20. And my current was 2.49 on the first run. And now I can record the numbers I see here. This was the run I just finished. So when it was up here, I had a value. This is my background. Magnetic field. We use the symbol B for magnetic field. And then I have the magnetic field with the current. So the background field is 7.02 times 10 to the minus 6. 7.02 e to the minus 6. And it's positive. Positive 7.02 times 10 to the minus 6. And with the field, with the current flowing, I've got negative 1.436 times 10 to the negative 4. Negative 1.436 e to the negative 4, 10 to the minus 4. Now I'm ready to do my next measurement. I'm going to turn the current down. I'm going to run it at 2.067 amps. And we'll go back and we'll take a data set. So I'll hit record. I'll reach over and hit tare. At about 8 seconds, I'll turn on the current. Now I'll turn off the current. I'll wait a few more seconds and I'll stop recording. So now I'm ready to get the information from this graph. I come up here and click on that little highlight range of points in active data. So I'll click on that and I can move it over here so it's a couple of seconds of data here, and I can stretch it out so I've got a couple of seconds of data here, and I only want the stuff up at the top. So I'm good on this side, but oh, I've got this extra point down here. I don't want that. So I'm going to move this up. There we go. So I've only got what's really the background data, and it's an average of 3.135 times 10 to the negative 6. .13, and now I'm ready to record the magnetic field with the current on. But you can see I've got this extra point right here. That looks like it recorded a data point before the field really turned on all the way. So I'm going to see if I can exclude that. There we go. I like that better. These points look like the current had already turned on and was established. So negative 1.281 times 10 to the negative 4. And let's do one more. Let me turn my current down a little bit. 1.573. Now I'm ready to take the data. I click record. About 3 seconds later, I hit the tare button on the sensor. That zeroes it. About 8 seconds, I turn on the current. I let it run for 6 or 7 seconds. Turn it off. Let it go another 3 or 4 seconds. And stop my recording. Now I can take the data here. I click on the highlight range of points. I can drag it over. I get a couple of seconds worth of data here and a couple of seconds worth of data here, and move this up. I don't want this point. That point looks like it's too soon. Let me move up a little bit. And I don't want this point over here. I'll try to exclude that. There we go. That looks pretty good. 6.136 times 10 to the negative 6. And now I want the average down here, but oh, I've got this extra point here. I don't want that. Let me rescale this so that I exclude that point. Now I just have the points that are at the bottom. That's what I want. Negative 8.745 times 10 to the minus 5. Now I will set up a column in my spreadsheet to take the difference between these two. So this is going to be B due to current. I'm going to subtract one from the other one. I think it's just easier if I have a positive number here. So I'm going to put an equal sign there to tell Excel that this is an equation. And I'm going to select the background, and then I'm going to subtract this magnetic field with the current. That way I get a positive number. I think that's just easier. It doesn't really matter. I can grab the corner and drag down, and it will fill these with the equation for this row and this one with the equation for this row. So there's the magnetic field due to the current. And I can create a graph. I can take this column. Let's see, it's easier for me if I just move it. I'm going to copy this, and I'll just click over here, and I'm going to do a paste special, only the values. If I just do a paste, the formulas will get copied here, and it'll be 0 minus this cell is 0, this cell is 0, it'll be 0 minus 0. I don't want that. I want this value copied and pasted over here. Now I want to copy my current. Those are just values I typed in, so I can just hit paste over here. So I have current and magnetic field due to the current, and I can highlight those columns and insert a scatter graph, no lines, and there's my chart. And I'm going to look at this and do some trend line fitting and see if I can come up with what that relationship is. Does the magnetic field depend on the current? It looks like there's some changing going on here. If this was a flat line, if the points were all fall on a horizontal line, then I would say the magnetic field does not depend on the current. This is magnetic field on my vertical axis and current on my horizontal axis. But this looks like there's some kind of relationship. And so then you have to find out, is it linear? Does it go as I squared? Does it go as the square root of I, right? We're trying to figure out what's the relationship here. You're going to do that for the data you get for the changing current. I provided you with more than 3 data points. Then you're going to do it when we keep the current constant and the number of turns constant, and we change L, so that'll be changing L. And then you're going to do it for changing N. So you're going to come up with a relationship to try to figure out what is the formula for magnetic field in a solenoid in terms of these 3 parameters. There's one more thing I'd like to show you, and that's how to flip back and forth between the different runs, the different data sets we've taken. If you look up in the upper right corner, you see we're looking at run number 3 right now, the last one we did. If we move over to the left corner and we click on this down arrow, it brings up the other runs. We can turn this one off and bring up run 2. Now we can look at run 2, take the data here, do what we need to do. Then we can always check in the upper right hand corner what run we're looking at. I come back to the left corner, click on that down arrow, and I can actually select all of them. I can have all of them displayed at the same time, but that gets a little confusing. Let's go back to run 1 now, the last one, and we can take a look at that. So you can always come back up here and switch to a different run. You can have 2 on at the same time. Turn that one off, turn that one on. You can cycle through the runs that you need to view.